Okay, morning everyone. Today I'm going to be a presentation about introduction on microfabrication. But just before the introduction for microfabrication, I'm just give you a brief introduction of myself. So about 18 years ago, I was start working as a researcher on MEMS in States. That's where I start on working on MEMS and microfabrication. So about after 4 or 5 years, I moved to Canada, start working on MEMS pure foundry. So that's how I continue working on MEMS as the R&D engineer and MEMS project manager. So on that one of the project I was working on is probably the one of the equipment you have been seeing that in the home, like say the Nintendo game console. When you play with this one, for example, for the tennis, the game, remember how you mess with your remote? Actually, we're working on this one on the R&D phase to volume production phase. That we exactly will make this gyroscope, this one. And I found it very interesting here. So after several years in the company, and about 5 years ago, I come to the Microfab working here. So you can see most of my time pretty much was involved in MEMS, microfabrication, and Cleanroom. And until today, I still find it very interesting. So I hope at the end of the presentation, you feel the same, not fall asleep. Okay, so let's get started on this one here. So today, I'm going to talk about the three topics here. At the beginning, I will just give you a very brief background and introduction, MEMS and microfabrication. And after that, I'm going to go a little bit of detail. So what exactly the microfabrication technique is. And then I'll show you a couple samples, some research works, and one of them is process flow. You can do that in hands-on part in the clean room. So for the background introduction, first we're asking, what is MEMS? You probably heard here and there. Some of you already know. Some probably not know much about this one. So MEMS stands for micro electro mechanical system. So which means the device has to be small, and with electro and mechanical components. And at the end, the device will integrate together and working like a system-like function device here. And take an example here again, the one you have used like 24/7, the smartphone device here. You may realize one of it has some micro device, MEMS device inside. Take example here, the microphone device. There are also one of the devices I have been working before in the company is the tiny microphone, like a membrane. That was how you talk in the smartphone here. Few more examples here. You pretty much can see this microfabrication application is in your everyday life here. For example, you have the optoelectronic one, the solar cell, the LED, the laser layout. Little far from this topic, but the second one, let's say you use printer, right? You have an inkjet printer here. The printer head is make a MEMS device here. That actually was pretty typical one. And you also have gyroscope, we just mentioned, for the remote control for the Wii console, the Nintendo console, and microphone, mirror, and you also have the application in microbiotechnology one, the microfluid device, which you're going to use in the hand-on part, and lab on chip, and you name it, so on. It was minor application for this one. Another example is not the cell phone that you use that often, but from time to time, you come to school or you drive to work. You look at the picture here. Actually, if you do the count, it was about 15 sensors here. This is how I made my MEMS device. This one here, let's take a few this one. The tire pressure sensor for the modern car. So right now you still have the tire pressure sensor here. And you have airbag one here to protect your life during some accident. And you have this one here, the silicon nozzle. So you can see here, many of the MEMS device actually was in your everyday life. Just for a snapshot of the car, you see how many of them. And you really just didn't realize this one here. So to make the MEMS device, we use a technique called microfabrication, and it was a micromachining technique for make MEMS device, and that was directly implemented from the IC fabrication. And so let's take back a little bit of history. What is the milestone part here? So the first one is on 1947. 3 engineers in their lab invented the first single transistor here. Do you remember what the, oh, maybe it was a little bit too, for some of you it was a little bit too young to know that. What has happened before that single transistor? What kind of device you have here? So, well, exactly, vacuum tube. So you happen to happen that one time you go into your grandparents' garage in the corner somewhere, like a reduced receiver, the old one, you can see the bulky, the power-hungry device, very fragile ones, tube here. So that was that time here, really huge ones. So that made this one, the first one here, really make this amazing invention here. So single transistor. And after like 10 years after, that was first IC come out here. And the first IC device is built in Texas Instruments by the engineer called Jack Kirby. So whenever working in States, I had the opportunity to have chat with him, and the story was told what's happening. The funny part, just told you the funny part here. At the time frame when he had come to this idea, it was summertime in 1958. It was 2 week vacation time for the rest of the engineer in the company, but he as a young engineer with no vacation, so he's stuck in the office, and they come to this idea. So what do we learn from this one? Don't take vacation. Your boss will be happy with that. And in year 2000, actually, he won the Nobel Prize for this one. Okay, that's the breakthrough, very milestone, it's breakthrough here. And after like 50 years afterward, so here, let's look at this one is the computer, the laptop you use. So you can see on single place you have the 2.27 billion transistor. It was huge number on this one, and that was talking about the small compared to this the Jack's invention here. Like look pretty ugly. It's like a garage work, right? Here a 32 nanometer in the future side. Imagine it's 32 really small, tiny device here. So that's just key milestone invention here. So now let's go a little bit further detail about what the fabrication technique is. So first look, we are going to build this one before we go the technique. We are going to do this one. So the first IC we saw that it's probably the garage work, right? It's no clean room. It's really big one here. But right now you want to build this one like the CPU, the Core 7. Not going to happen. So you have to have some special environment. That's what we call the clean room. So that place you have very tightly control for temperature, the particle number, the humidity, the lightning, the flow or pressure, or the vibration, and also electronic discharge and like a magnetic field, so on. So a lot of things is well controlled in that room here. One of the traditional way to name the class level, the clean room, you may hear people saying class 10, class 100, class 1000. The old traditional way we just the number of the particle in this room. A snapshot for the Intel 25 nanometer plant here. And this is the layout for our clean room, which will be used starting on this afternoon. So here we had 1,000 square feet. We had class 10. Unfortunately, it's class 10. It's not 10. Class 100, not 10 and 1, and class 1,000 here. So this area here is what we call the yellow room, which you're going to be spend your time on the hands-on part for the lithography part. And this area here we call white room. It was class 1,000 as you do most of your deposition and etching. You may notice the difference. The light is different, right? One is the yellow. And that reason is because, as I said it was in previous slide, you had a light control because your photolithography step, you want to keep on certain wavelengths. You don't want the wafer accidentally exposed. So that's the reason for this one here. That's why I said the lighting control here. How can you keep the room clean here? So few effort had to keep. You need to use filtered circulate air, and you need the positive pressure, which means that clean room pressure was higher than the surrounding area here. And you need to wear this one. So be prepared to wear this one here. You may want to take some outfit. It's going to be a little bit hot when the first time, and you need very clean water, gas, and chemical. When we buy chemical, we ask for like a VLSI grade, clean semi-grade, not just a light grade, and clean room compatible material. So what that means, the material has to be, made less particle. For example, the notebook we use called clean room notebook, not the regular notebook. So that's how we keep the room clean when we are to do this microfabrication. But what we're going to use for this one here, we use what? We use basically about 90%. The fabrication is started on silicon wafer here. We use the silicon wafer to make the device, and you have different sizes. Right now the technology can go to on production is 12-inch, and I have one wafer I'll show you. With some patent in my device. So that's about 6-inch size. So imagine 12-inch. It's going to be that size, that big. So you will have even really heavy to carry this one here. I remember one point when my colleague, when we start for the 8-inch conversion from production, and just pick up the wafer because he's not used to that. He just break that one. Where it's 8-inch and was a pretty expensive one, so you can just pass it around for the 6-inch wafer. And you can also use sulfide material as a substrate, and you can use a glass wafer. So that's how you use your substrate to make the device. Now it's time we go to a little bit detail. So what kind of fabrication technique we're going to use? We break this like 5 categories here. The first one, the property modification. You do diffusion and ion implantation to change the property of your substrate or the deposit film. And then you have the patterning, as like in Davis' presentation. We also call the lithography one here. So you make a pattern. You transfer a pattern from mask to your substrate. We're going to cover more detail on this topic. Subtractive one here. Normally we also call etching step here. They have wet etching and dry etching. Additive, basically you deposit a layer, you add a layer, and that one is you remove something. So this one you can do oxidation, PVD, physical vapor deposition, chemical vapor deposition, and the process. You're going to connect to the outside world, use packaging. So I'm going to talk about mainly on this one, and going to cover also these two as well. So we start with the patterning, the photolithography step here. The goal for this one is to you temporary coat of photoresist on your substrate, and you want to transfer your pattern from mask to photoresist, and then from photoresist to your substrate. That's the goal for this step here. And why this step is very important? Because it take about like 40 to 50% your process time. Let's say you have one project, you take like 4 weeks. So about half of the time you're going to spend on this one here. You're going to keep doing different repeatable steps on the photolithography step here. Of course, it's not on the same mask. It's multiple mask process here. And another reason to make this one very critical is because this step decide what is going to be a small future size. And that was one of the mask here. So also I have the one is the 5-inch mask here. So also we have 7-inch mask as well. This just give you an example of how the mask look like here. It's basically a chrome deposit of a layer of chrome on the glass substrate. So what is the detail for the photolithography step here? So let's assume you start this one here with the silicon wafer with silicon dioxide film on top. That's your starting substrate here. The first step, you do a cleaning. You want to make sure your wafer free of contamination and particles. And then you spin coat. You coat a layer of photoresist. And you do soft bake. You remove the solvent in the photoresist. Get ready for the exposure. So you bring the wafer to the exposure tool. Exposed by UV light. And after exposure, you do the PEB, we call post-exposure bake here. And in your case, you use SU8, you absolutely need this step here. And then after PEB, you bring the wafer to developing. So you can see what's happening on this step here. The area exposed by UV light, dissolve, being removed. You have this pattern on your photoresist. And you do another step of hot bake. And again, this step here, two purposes. One is continue improvement, the addition between the photoresist and substrate, and remove additional solvent. After hot bake, the step is pattern transfer. Actually, is the etching step. You transfer your pattern. You can see here that's pattern from photoresist here, right? And then you transfer this one by etching. The pattern transfer to the silicon dioxide film. And then for the resist step, at the purpose at the mask finish, so you can remove this one. Eventually you get this pattern, well, exactly like your mask one here. So that was all the sequence. You get this photolithography step here. Just show you in our fab, you have two equipment here. They both do the job for spin on photoresist. The spin coating here. That's how you coat photoresist. Little bit, animation here. So you do dispense your photoresist on the wafer, hold by vacuum chuck, and then you suck back a little bit photoresist. Otherwise, a little drop make your wafer coating is not uniform. And then you start to rotate. The wafer chuck start to rotate. And at the end, you're going to have uniformly coat certain thickness of the photoresist. And after you coat your photoresist, you bring your photoresist coated wafer to the UV exposure tool here. Typically, there are three types of the exposure technique: contact, proximity, and projection here. The contact printing is your mask actually was in contact with your substrate. Then make sure you have, this way you make sure you have better resolution. And this one, they have a space here. The benefit of this part is your mask and the wafer was not really contact. So then make sure your mask, it was not really easy to wear out, and also there was no contamination, keep because stick your photoresist to your mask. And both had, advantage, advantage depending on your application. And this is the one actually was what happening is it's kind of like industry standard here. Is we usually have a stepper here. So the result for this one here, the mask side and wafer side, the pattern on the mask and the pattern eventually get on the substrate, actually was a 4:1 result, 5:1 result. So you can have this side much bigger than this one here. And the step repeat and really fast process. If we have time to look for one of the kind of like famous video on the YouTube, which we have downloaded here, you will see exactly how this one working. And then we go to the developing part. We code, then we're going to develop. So developer show the photoresist, the soft part, exposed part, from the rest of the photoresist, but really depend on you, negative or positive resist. That's the difference. Then you transfer your mask pattern from mask to photoresist. We already see the step there. And you develop, you rinse, you dry your sample or substrate, you make the process finish. We can either do the automatic way, or we can do manually in the wet bench, manually developing, like old day you develop your film. And we just mentioned about photoresist part, which area being removed or washed away during the developing step. That will really depend on what kind of photoresist you use here. And photoresist is a type of material, change the molecule structure after exposed UV light. And if look for this schematic variant, right side is mask, same. But if you use positive resist, so what happens is the one area exposed by UV light being washed away during development. And if you use negative one, so the area exposed by UV light actually going to be stay here. No exposed area will going to be washed away. So that's pretty much is the patterning technique we're going to use. And just a little bit advertisement for the microfab. So we have a few different patterning technique. One of them is called laser writing. So in the aligner, in the UV tool, we actually using the mercury UV lamp. It was really a lamp here. So instead of that, we use a laser exposed photoresist. But that one, again, its benefit is one, you don't need to make mask. So you design your layout, and the machine will really make this one. It was good for fast prototyping here. But on the other hand, it was kind of like a long process. You're going to draw the pattern one by one. If you need a volume production, it's not really good too. You better make a mask. So everything was done one shot. Everything, you had a photoresist out pattern pin out. Here, you're going to draw everything here. Another one we have here is the electron beam lithography, which again, instead of the mercury lamp, later we use electron beam. The principle is the same. We use this one, and we use the electron-sensitive polymer. It's different type of photoresist. And the benefit for this one is, again, there was no mask need. And you tend to have small feature here. So far, the best one can get down to the 30 nanometer small feature. The most recent one is another new one, is thermal scanning probe lithography, a tool we call the nano freezer. So this one, instead of UV lamp, laser, E-beam, actually was using the scanning probe, heat scanning probe. So what happened is the probe actually in contact with one type of polymer called PAPA, I actually burn this one, make the polymer decomposition and evaporate, and make nanometer range structure like this one showing. So the structure here, you have the reading pass here, you have the writing here. So basically, you are going to heat this tip to burn the polymer here. So we just cover for the patterning part. I'm going to talk about a little bit subtractive process, the etching step here. So in MEMS device, you're going to see some like a membrane floating here or cantilever beam. You need to make this structure release. You need to remove something. So there are two ways here. We call it either surface micromachine or bulk micromachine. So surface one actually remove the deposit film like this one. So you actually remove this part here. The bulk micromachine actually remove the substrate in itself like this one here. You actually remove the substrate itself here. Forgot about the line on top. And etching process normally divided by two classes. Typical one is we call the wet etching. Pretty much, as the name said, you need a chemical solution. That's this one here. Dry etching, which was etching that was more gas phase, dry. It was no liquid, no chemical. Normally use like a reactive ion, plasma, and all wafer phase. And normally it was single wafer process. And this guy, white etching, was more like a batch process, which means you can do 25 wafer or 50 wafer in one of shot. The white etching normally performed in the white bench here, and it was more chemical solution. Usually it's isotropic. What I mean by isotropic is, remember I said in the previous slide, you transfer your pattern from photoresist to the substrate. So what in reality going to happen? In schematic layout, you see that you have perfect vertical sidewall like that. But if you do white etching, you tend to have this one here. That's how the isotropic etching happen here. That's in reality. White etching also, very high etch rate, but they have some, resolution limitation. That's the few SEM image. So you can see that some release structure, and that was common dry structure here. That's released by white etching here. And on the other hand, it's dry etching here. Gas phase, and with sparkling and chemical etching happen at the same time, and more for anisotropic etching. So it's not like you're going to have a directional etching. You have high resolution, but it's a single wafer process. And that's showing what it really happened during the dry etching, more reactive ion, plasma, the complicated reaction. You may don't want to know about this one here, but just remember this one is dry, no liquid, and tend to have the isotropic etching. A typical example, and a very famous one is Bruce process. We call it deep reactive ion etching here. That's the system we have here, this one. And that's the isotropic etching here. And you want to make this one happen here. So that's these two can do that. So how this would exactly happen here is you get two gas. One for etching, one for deposition for the protective layer here. And you can alternate changing etching step and deposition step here. And also you get the ion bombardment to the bottom to remove the bottom layer, bottom polymer layer here. And look this way here. So what exactly happening here? You start with etching chemical here, etching gas here. So you make this profile, and few milliseconds afterward you deposit here, and then you etching directly to the bottom part, and then you repeat this one again. So what happens is you can do etch, deposit, etch, deposit, etch, deposit. So you gradually you get this profile. You don't really see that by your naked eyes, see these trees, but if you look for the, take this example here. If you look for this one for ICM again, you can tend to see these trees here. It's we call the scalloping effect here. So this structure, you can see the vertical, nice vertical sidewall here, and it was kind of 200 micron here. That's made by the DRE step here. Just to give you an example, you know how nice the dry etching can do. So here, I think the process, life cycle deposition step here. So again, there was many category here. Typical one is called physical vapor deposition. Another one called chemical vapor deposition. Atomic layer deposition, ALD, and electromechanical deposition. Example, electroplating. So we had all the capacity in our fab. Example, for the thermal oxidation process, that's one of the one you're going to grow a layer for oxide. So this mostly happens in a stack. In the stack we call the furnace here. So they see the furnace stack here. You put your silicon wafer in the furnace at high temperature. You have two chemical reactions happen here, depending on you use dry oxidation or wet oxidation. That's how you grow a layer of silicon dioxide. That's what we call the oxidation one here. Another typical one is evaporation. So what happening here is you use electron beam, the filament, to heat the target material in the liner and melt this one, and you make this material evaporate on the substrate here. And we can do many types of metal here. Gold, imagine gold, the melting point pretty high. By this technique, you actually can see that the metal will actually like liquid, act liquid. Vapor evaporate, you can coat this so far this material in our fab here. It's more directional, so whatever you see in the line of sight, like that. So I just gave you a few example for addictive process, since you don't really going to be used for this hands-on part, but I'd like you to have some rough idea on this one here. So far, I've been talking about patterning, the etching, the deposition step here. So this step is likely, this, when you have a complicated project, and we're talking about maybe 10 or even like 15 masks. So this step will be repeat and use and build up or take down different layers. Etching and deposition, that was combined together by different sequence here. After this device being fabricated, like I said, you need to connect to the outside world and protect your device here. So just one slide about the packaging part here. After you make your device on that right side, the one I just passing around, the 16 wafer here, you have so many identical devices, and what you can do is you're going to use a dicing machine to cut each individual piece, like the one we just saw here, and then use wire bond to bond this contact pan to here, to packaging. And eventually, you're going to put in the packaging. You not only connect to the outside world, also the device may be exposed to extreme temperature. extremely like a harsh environment. So you can protect also the device, connect and protect. So pretty much that's the rough idea. You from the very beginning, the starting wafer to the front end to back end to really get you stuff like that, like the packaging part here. Just some the sample part here. So well, that's some. We have many image with restriction of time. I'm just going to show two here. One is PDMS microfluidic device, and it was actually from David's group here. And the second one is the indium nitride nanowire LED. It's from JDS group. This is our research achievement from our fab here. This one we're going to talk about, the one you're going to use to the fabrication in the microfab here. Normally, when you do a project, so you need to think of two phases. First, like the design phase. In design phase, you're going to think about your process flow. What I mean is you're going to do which step first. For your case, it will be simple, just one mask. So you don't need too much thinking which one go first. That was really sometimes critical. You can switch the order, do this first, that second, that make a lot of difference, and also make your process flow be more feasible. You need to see what tool is available. What is the limitation. The reason I said the limitation and also the layout inside your land space, the future size, is something you have to think about linking between design and fabrication. So when you design something, you can design whatever you want. Like say, I want to 0.1 micron future. I need that device to be 0.1 micron. In design phase, that was no problem. You can do that. But like I said, you want to make this happen, fabricate this one in the clean room in the downstairs. And I can tell you for the photolithography step, like I said, the UV light, exposure tool, I tell you it's not going to happen because that was a limitation for the tool. So a lot of things you have to think about, and in your design phase, what is going to happen? Is that durable in the fabrication step? And what is the future side and height, as I said. Once you have to think about this part, and then you have to, on the fabrication phase, you prepare, okay, what are going to substrate I'm going to use, what the photoresist I'm going to use, and the mask, I choose 5-inch, 7-inch, some detail you have to think about this one here. That can make your life much easier doing the process part here. And what equipment available? What equipment can we do this certain job? For example, I want to do the pattern transfer. Remember I said etching? You can do two ways. Wide etching, dry etching. The boss can choose. Sometimes you have to choose one of them. So the two phases, you have to think about this one carefully before really start to working. This is the one actually you probably already see on your brochure here. So I just want to quickly go over that part here. You see here, the step name here. So that was exactly I was talking about in principle in the photolithography step here. So first, I'm just over here. You do the cleaning, right? Remember we do the cleaning at substrate. And here I have HFD here. So what are the purpose for? I can still put it in the category for the cleaning. This job is just to remove the native oxide from the silicon wafer. And then you coating, right? You coat the photoresist. You do the bake, exactly, and you do the exposure here. Here, exposure tool is a mask liner here. It's not stapler. It's just like one visual mask here. You do the soft contact exposure. And you do the PV, right? We saw that, and you develop it. And you dry it. You dry your wafer, and you don't have bake. If you remember in previous slide, the principle, it was exactly follow this step here. And here I'm just talking about the principle. So you're going to see that exposed to that more in the hands-on part. So I was hoping, by this slide, I can give you some slide the idea before you go really down to the basement, of microfab. You have some preparation for this one here. So that's going to be all my slides part. So I have the video actually, which you also can find out in the YouTube. And what's so far I think is a really good one. I can see the well explanation, and you can see the modern technology, the clean room, and I also explain some, the basic process.
It's good.
Yeah.
Sweet.
Yeah. So this one, this is the one about the TSMC.
You can just click when you're ready.
Yeah. So this one is the video made by TSMC, Taiwan Semiconductor Manufacturer Corporation. Would I better?
Yes.
Okay. So that was the company is if you know this field, the company is the giant, the big guy in the field for the pure pearl foundry, which means they're only doing the fabrication part. I don't do any. Pretty much I don't do any design phase. So you give you your design. I do the fabrication for you. But I had a design rule. You have to follow my design rule. You cannot do design whatever you like. I tell you my small future, I can only do 45 nanometer. So anything below that, somewhere else, that's impossible. So I have in 20 years ago, I had the chance to visit one of the giant plant, and really nice. But that time it was 2011 here, but I was talking about 20 years ago. That's different. So technology, the wafer is already size is different. You already see it's gonna be pretty much different.